Good evening, everyone. I'm Iwei. I'm a Ph.D. student in the faculty, and I was a ChangeMaker here 3 years ago in person. And right now, today, I'm the Master of Ceremonies. It was really cool to be back here in person. I remember last time when I was here, it was already 3 years ago. Didn't expect it to be shut down. But throughout the years, we have the online events, and if you missed that, please check out on our website. And we would like to extend our welcome to you today. And it's really happy to have all of you in person, and really glad to see you to be here with us today to enjoy the talk this evening. So we are also pleased to announce that Sedtalks 2022 is sponsored by WSP, which is a leading global professional service firms. At a few moments later, you'll be hearing from Mr. Eric Pesel. He's going to give a talk about how WSP is really committed to sustainability and their decisions to support these initiatives. And before we start, I would also like to acknowledge that McGill is situated on the land and territories which used to serve as meeting places and exchange for the indigenous people. We would like to acknowledge and thank the indigenous people who has a diversity and mark the territory here so that we all from all over the world can be here, gathering here today to learn and exchange knowledge. And it's really glad. And also for those who don't know about Sedtalks, it's an initiative that TISET started to highlight the researchers that the graduate students in our department and faculty is doing, which is in the topic related to sustainability. I remember back in 2018, I was one of the participants in this program. I went through a lot of trainings in terms of how to give good communications, how to present my very complex research in very simple messages so that it can impact a lot of people. And throughout that training in the fall semester, we had a presentation right at the end. And the judges will choose 3 ChangeMakers of all those participants to give a lengthened talk. So the 3 participants that you'll be hearing today, they went through a lot of personal coaching and training in a TEDTalks kind of style so that they can be ready to give you a good presentation and good stories today. We hope that today you will be able to enjoy the fruit of their labors and be able to feel the impact and the passion they have in changing the world. So hopefully today you will be here to be able to enjoy the talk. And I would like to invite the Dean of the Faculty of Engineering, Jim Nysel, to say a few words for the faculty.
Thank you, Yue. It's a little daunting. This is the first time I've spoken to an audience in over 2 years, and I used to do it on a daily basis. And then to have my cold opening on a night that features the best of communicators is just a little bit much. So I just want to say thank you, first of all, for all of you being here, I guess, in the tail of the pandemic. This is a very special occasion where the Sedtalk event is really going to celebrate some of the great work that is being done through TISET by our students, working, of course, with our professors across the faculty and the university itself. The Faculty of Engineering and the university are deeply, deeply committed to sustainability, and I hope you see that reflected in so many different ways. It's reflected through the establishment of TISET itself, with the goal of actually bringing together researchers from across disciplines and across faculties and with partners to work on really important issues related to sustainability. These are very complex problems, and they require people who are ready to work together to communicate with each other to bring their ideas to reality. Beyond that, we have educational initiatives incorporating more and more about sustainability, weaving it throughout our programs. And very importantly to us, the master's program that TISET has worked very hard to develop is now entering the final stages of approval with the government of Quebec. And then beyond this, of course, you might also be aware of the important work that's been done on the operations of the university itself. we, as the biggest real estate owners and operators in the entire province of Quebec, have a really important role model to play in exhibiting what the best of behavior, the best of changes are within infrastructure to actually support sustainability for the long-term future. Today is about conversations. It's about communications. Now, this is a communication episode where people will talk to you about their great work that they're doing. For me, very pivotally, I guess I'll say that communications, I think, is at the root of engineering. I've often said that engineering education is the best liberal arts education you can get. And I will say that because you are forced, in a way, to encompass all these concepts of science, to integrate them with the whole process of design, in stakeholder engagement, in economics and humanities, and work it all together to produce your magic that is the technology of the design or the built environment that you create. That's really, really important. But communication isn't just essential at the final stage of your work when you're introducing people to the fruits of your labor. Communication is absolutely essential up front to understand the stakeholders' needs. What are you designing and why are you designing it? What are the priorities that you're trying to address? What are the needs? What are the potential problems, the challenges that you need to think about? And communication even unfolds after that. In the entire process of pursuing your research, pursuing your designs, you have to, in a way, iterate back and forth with your stakeholders to make sure that you always fine-tune your work so that when you come to the end of your project, you're not just ready to tell them what it is you did, but you need to be able to respond, to show that you did respond to their needs. And then, of course, through the entire implementation phase, communication is an ongoing issue. So I really, I guess I'm very proud of TISED to say that they put such a central focus through Sedtalks on the importance of communication, which is really central to all our roles, whether we're engineers, architects, or urban planners. And it's not surprising, I think, for Eric Picel to be here because, one, as an alumnus of McGill University and our faculty, but two, as somebody who has a very important leadership role in this internationally important company, WSP. They have an absolutely pivotal role to play when it comes to the infrastructure, transportation systems, all the systems that we work with, that we play in, that we live in. And so it's not surprising to me that they have a very strong commitment to sustainability as well. And so for this reason, I'm very happy to have Eric here today to actually explain why WSP came forward to actually make very concrete contributions to make this possible, and why they're such a great partner to the Faculty of Engineering. So over to you, Eric. Thank you.
Hello, everybody. So a lot like Jim, this is the first time I get to address a three-dimensional crowd in about 2 years. So it's a bit of a surreal experience to be doing this again. So I'm really happy that it's actually at my, as you heard, my alumni McGill here. I'm an urban planner by trade, so I do come from the Faculty of Engineering, just the kind of a small little part of it that, you know, since our degree is a Master's of Urban Planning, everyone calls us Muppets for MUP. You know, listening to Jim, one of the things he said is absolutely true, is the importance of communication. And I would say, actually, this pandemic has shown it even more, because, in fact, it's even more difficult to communicate when you're not face-to-face. And the importance of being able to properly communicate, to understand issues, and convey them, I think, is a great theme. And again, something that's great with this as well is really gives real-world practical applications. Because, in fact, you can be the best engineer in the world, you can be the best architect and the best urban planner, but if you can't understand the needs of your people, of the clients, of the governments, and be able to relay that back into solutions that are meaningful, then you're not really able to move things forward. You know, as I said, I'm always happy to be back here at McGill. I've had the opportunity to guest lecture, be here for various events as well. And in fact, as a consultant, I got hired a couple times by McGill. In fact, walking up here, it was great walking up McTavish, because one of the projects I did for McGill University was the pedestrianization of McTavish Street after the City of Montreal gave it to the university. And I remember talking about communication, endless meetings with the City of Montreal Fire Department to convince them that closing this street to pedestrians would not be a catastrophe, and that we could design it with benches and make it nice and still allow a fire truck to come up if something starts to burn down. And you know, we did a temporarily pilot project, and it's great, you know, walking up now to kind of see the final product that's out there. And but it also talks to the sustainability that, you know, McGill is trying to do as a campus. You know, create a campus that's really pedestrian oriented And that's another big project that I worked on with the university, which was removing cars. Many of you might not remember, but in fact, you used to be able to park all through the campus, and through the rotted gates, you'd walk in and you'd be able to pay for parking. And so removing all of that was another project I worked on with the university, and that was entertaining. Biggest issue there was dealing with different professors who didn't want to give up their parking spot right in front of the building. But the fact that we've been able to change kind of just shows how the world has really evolved in its thinking. And, you know, WSP, the real reason that we're here supporting Sedtalks, as well as Ty said, is part of a larger engagement that McGill and WSP have. You know, WSP is the largest Canadian engineering firm. We have, you know, over 55,000 people around the world. We have about 10,000 alone in Canada, headquartered right down the street at the corner of Galih and René Lévesque. And for us, we've been on a long journey as a firm because we kind of have three big businesses. The one I lead globally, which is transport and infrastructure. Earth and environment is our second largest one around the world, which really talks all about environmental sciences, about water, about clean air, about ground. And then our other one is property and building. So we really touch all aspects of the built form. And probably back in 2017, we launched a program called Future Ready, which goal is very simply is to see the future more clearly around kind of four big themes, which were climate, society, technology, and resources, and talk to our clients, going back to the theme of conversation. Because often, you know, our clients come out with a project and put a request for proposals on the street, and we reply to it. But once we win these projects, we try to actually talk to our clients to say, have you thought of the bigger picture? Have you thought how you can make your infrastructure more resilient? How you can meet the demands of the future today? Because if you build it in today, it'll cost you much less than trying to retrofit in the future. And it's something our firm has been doing over the last 5 years now. And you know, for us, it's something that we find that resonates really well with our clients. And in fact, I would say the interesting thing about COVID is when we first got into COVID, talking to a lot of our environmental teams, they were really concerned that the momentum around sustainability, around resilience, was going to slow down. And in fact, I would say over the last year, COP26 really actually galvanized. So, you know, something we've been pushing for a long time, we were kind of concerned may take a back seat because of COVID. And it's great to see actually the renewed energies around there. And you know, WSP as a firm, we've made our own commitments. You know, we want, right today, of all the business we do, 43% of it is considered clean revenue. So it's environmental, it's water, it's really dealing with renewable and sustainability. And as a firm, you know, we've committed by 2040 to have our entire supply chain get down to net zero. And that's really based on a science-based GHG emissions approach, as you might expect from an engineering firm. We just didn't put a pie-in-the-sky target. We actually figured out how we were going to do it. And that is really to make sure that we align with the Paris Agreement's 1.5 degrees Celsius. But I would say even more important than our goals as a firm, because, you know, as an engineering firm, yes, we do have a certain footprint out there, but, you know, we're not a large polluter. In fact, where we can make the most difference is with all our different clients. As you heard, you know, we advise the largest ministries of transportation, departments of transportation, the largest property owners on the planet, and government. And in fact, we're working very hard with all of them to understand how they can actually turn their objectives, because there's been a lot of great objectives that have been thrown out there by private industry and by government. The reality is when you talk to them, they don't know how to get there yet. And so that's one of the things we at WSP have been doing, is really sitting down with those clients and discussing with them how can they achieve those net zero goals, how can they meet the sustainability objectives they have out there. And for us, it's been a great journey to really kind of sit down, walk and work with our clients on that. And you know, another big reason that we're supporting McGill and all of these great programs is for us, as the Canada's largest engineering firm, you know, we need the next generation that's going to come in, that's going to help us continue this work. Because, you know, getting to net zero and getting to be sustainability is not a luxury we can afford. It's something we have to do. And so as a firm, we want to have like-minded engineers, and programs like this is just great to have people focused and thinking about this. And you know, the master's program, I wrote a letter of recommendation for that, and it's something I hope that gets approved soon, because for me, it's where this industry is going, and us as a firm, we're strongly committed to that, as well as the larger, if you kind of pull out of the environmental and sustainability the larger ESG part of the equation, which is also around society and governance as well, and making sure that we bring the whole picture around. And I was really happy to hear the acknowledgement at the beginning of this session, because it's really important to also look at this from a lens of society and equity as well. So with that, I'm really excited to be hearing from our three change makers. I read kind of the synopsis before I came here, and they really sound like some great, interesting talks that we're going to hear here. So without further ado, I'll turn it over. Thank you.
Yeah. Thank you, Jim Nysel, the Dean of Faculty of Engineering, and also thank you, Eric Pessel, who is the Director of Transportation and Infrastructure at WSP. Yeah. Thank you, everyone, to be here today. Before we start into the talks, I would like to have a few words about the format tonight. Tonight, we will have the three change makers each come up to the stage, and they will give 15 minutes of their talks. And in order not to disturb the flow of the event tonight, we'll leave the Q&A sessions with all three change makers on the stage after the last presenter have presented their talks. So if you have any questions, we will ask you to leave it until the Q&A sessions. And if you have any need of leaving the rooms throughout the sessions, we ask you to wait until they finish giving the talk and do so in between the transition of the speakers. And also, we will also remind you to always keep in mind the health measures that we have in place for here so that everybody can enjoy the talk tonight. All right. And now, without further ado, I would like to invite our very first speaker up the stage. Our first change maker of the evening is Anirban Kundu, who is a PhD student in the Department of Civil Engineering, under the supervision of Professor Subhasis Ghoshal. And tonight, Anirban will tell us about how to improve the efficiency of cleaning up diesel contaminated sites in Canada. Anirban.
What comes to your mind when you hear the terms oil spill? Maybe this? I agree. Oil spill is usually a term that's coined with an oil tanker in the middle of an ocean, vast volumes of oil that look very pretty like a rainbow from the top, but actually at the bottom it's a dark, murky story. The animals are frightened, they're scared, they don't know what to do of this foreign substance that's entered their environment. In fact, that bird, that's a very famous bird, even though it's in agony. That bird was pictured from one of the worst oil spill disasters in US history. However, oil spills may not only occur in water. They can also occur in soil, in the land. These oil-contaminated sites have similar devastating impacts. Canada has more than 4,000 plus oil-contaminated sites, which brings the question, how do we clean up these sites? Well, as engineers, we have a number of different methods, but broadly, they can be grouped into physical, chemical, and biological approaches. Let's go over each of them. So what are physical approaches? Well, these approaches mainly look towards containing the oil, or maybe excavating a part of the land and treating it elsewhere. If you guessed it, you're right that these require a lot of infrastructure, manpower, equipment. Thus, while they may be okay to use in regions in normal climates, they're very difficult to be used in remote regions in the subarctic because of cost. Thus, they are not sustainable. Chemical methods, on the other hand, rely on chemicals to clean up the spill. This actually sometimes works, but these chemicals are worse than the spill itself. They are toxic, they are harsh, and they render the land clean, but totally not in use for agriculture. They disturb the biota. They are very, very toxic. Thus, they cannot be used. Biological methods, on the other hand, rely on the microbes, the bacteria that are already present in the soil to clean up the oil spill. They rely on the indigenous bacteria. Thus, they can be applied anywhere, here or in remote regions. They are sustainable, they don't have any toxic impacts, and thus, this is a good approach to follow when cleaning up oil spills in a sustainable manner. This leads me to delve into how a biological treatment takes place. So the oil spill, in the onset of an oil spill, in a biological treatment, we add nitrogen and phosphorus to stimulate the growth of the bacteria. Keep in mind, all living organisms, you, me, the bacteria, we all need a ratio of C, N, and P to survive. Carbon, nitrogen, and phosphorus are the building blocks of life. By supplying nitrogen and phosphorus, we are stimulating the growth of the bacteria, leading them to increase in number and cleaning up the spill. So let's go over our bioremediation pipeline. So you have an oil spill, you add nitrogen and phosphorus, the bacteria grow in number, so far so good. But even though we did all these steps, there is still a fraction of sites that are uncleaned. There is still residual contamination in substantial amounts in a number of sites. Why is this so? Why is it that despite following all the steps, we still don't have good cleanups? And to answer this question, let me give you a magnified view of what happens in the soil. So this is a simulated diagram of an oil spill where you see the bacteria, the Pac-Man, you see soil moieties, and you see the oil spill. Now in the onset of an oil spill, oil is a carbon source. And it tells the bacteria, come, there's food, let's grow. And you add the nitrogen and phosphorus, so the number of bacteria, they increase. The bacterial count increase, the oil, they slowly start consuming the oil until the volume of oil shrinks where it is only present in tiny pore spaces within the soil. Now the bacteria, they want to access this oil, but they cannot because the entry points are very small for the bacteria to go through. At this point, it is not a food problem. It is an accessibility problem. And bacteria, they need food to survive. So they will go to alternate carbon sources, like soil organic carbon. And this residual oil remains sequestered in these cavities undegraded. Residual contamination that was not bioaccessible is undegraded. And this is the problem that I am trying to solve in my Ph.D. using a combination of microbiology and geochemistry. Now that we have set the stage, let me take you to my lab. So in the lab, I work with contaminated soils from subarctic Canadian regions, mainly traditional First Nation territories. Why? Because they still rely on diesel for their power source. These regions are so remote, the transmission lines cannot access these regions, leading to contamination. And this is the contamination we are trying to address. So in the lab, I start by microcosm experiments. You remember when I said you add nitrogen and phosphorus to clean up the soils? We are exactly doing the same thing, only in small glass bottles. From these reactions, I do two types of analysis. I do bacterial community analysis, broadly trying to answer who are the major hydrocarbon degraders, how are these bacteria present between the soils, and so on. In parallel, we also want to measure the bioaccessible and inaccessible scenarios. So we want to measure the submicron habitats from these soils. Let's start with bacterial assemblies. What are the two main questions we are trying to address here? Who are the major degraders? How are they different between or similar between the soils? What are the trends between biodegradation responses? That's what we're trying to answer through this analysis. And to do that, the first step is to understand the biodegradation responses between the different soils. These are results from microcosm experiments. Along the y-axis, you have the percentage of contaminant remaining, and the x-axis is time. Please note that these experiments are all done under actual site conditions, the same temperature, moisture, everything is the same. We are mimicking whatever that's happening in the site in the lab. And we see that in case of Suwito, two things happened. Number one, the overall biodegradation was phenomenally good. More than 80% was removed over 50 days. Number two, adding nutrients actually helped, as opposed to not having nutrients. However, that's not the case in all soils. In 4 of them, the biodegradation response was okay, not too bad, not too good. However, the 3 soils really had very poor biodegradation. More than 60% of the contaminant was still present after 50 days. This is what we had anticipated, right? Different biodegradation responses from the different soils. So now let's try to see how to characterize the bacteria that's present in the soil. And to do this, we follow a very high throughput, a very detailed approach. So I start by extracting the soil genomic DNA. I then sequence the DNA using high throughput molecular biology methods. And for sequenced information, I resolve that using computer scripts. And what that tells us is, it tells us patterns, it tells us trends. Who are the major degraders? For example, the blue Pac-Man, the blue bacteria, seems to be associated with a much higher biodegradation extent. So soils that would have the blue bacteria should have higher biodegradation. The red bacteria on the other side is not a good member in this category. This is the result that we are trying to get from this analysis that is right now ongoing. Once we have measured or analyzed the bacterial community, we also need to analyze their submicron habitats. So what are the major questions we are trying to answer here? Well, number one, how can we quantify these habitats? These habitats are really small. We are talking at the micron level. And number two, what are the correlations between this submicron characterization and the field data? What correlations exist? So before I step into how to characterize these submicron habitats, let's remember, we want to preserve the structure of the habitats while characterizing them, because space is a major factor in these habitats. So we need non-invasive methods of characterization, and we do that using X-ray microcomputed tomography. That is basically the CT scan that we all have heard of, except at a much, much higher resolution, right down at the micron level. So we take a sample, we shower it with X-rays, and we get two-dimensional cross-section images. Once we get these images, we recombine them back to get the original three-dimensional soil. And from there, we can understand, we can interpret the bioaccessibility and inaccessibility extents. This is what a X-ray microcomputed tomography setup and result would look like. Where you see on the left, in that small box, that's my sample. That's 1 grain of soil that had to be carefully isolated, as if I was playing football, and put into a nice small support, and keep it there so that it doesn't break, nothing happens to it. And we are imaging that using X-rays. And what we get is, we can see the soil, we can see the pore spaces, that's the gray part, and we also have the rock and the mineral debris and so on. What are we trying to get out of this analysis? Let's look at soil like a network. It's like a network of roads, highways, freeways that you encounter when you come to work from your home. That's the brown network, that's the soil. If this network has a lot of broad roads, broad alleys, highways, it's easy for the bacteria to access these roads, leading them to degrade the contamination that is present. However, if the roads are constricted, narrow, extremely small for the bacteria that they cannot access, then the contamination remains in these cavities. And to quantify this, we have two parameters, porosity and pore connectivity. So let's go a bit deeper into what are these two parameters. So what is porosity? It is the fraction of voids that are present in the soil. In simple terms, it is the number of pores. However, that's not useful in its sole sense. By knowing the number of pores, you can only answer, okay, the amount of space available to the bacteria. But hey, you need to know how these pores are connected. That is why the pore connectivity is very important. Knowing how the pores are connected can tell us how the bacteria can access the various regions within the soil. And to answer that, we use a metric, or we depend on a metric called Euler connectivity. Now let's go one step deeper to understanding what is Euler number. Euler number basically gives us a measure of the ease of bacterial accessibility. The more negative your Euler number, the more interconnected the network is. Now let me take you back to the bigger picture. If you have a soil where you have very good porosity and very good interconnectivity, I would expect excellent degradation. Why? Because the bacteria can access all these pores. It's so easy for them to go around and clean up the contamination, provided, of course, you add nitrogen and phosphorus. But if you have a soil where the porosity is very low and the pore connectivity is also not good, then you have isolated islands that are contaminated. And bacteria cannot access these islands because the road doesn't exist, or the road is too small for them to traverse. This is the question that we are trying to answer from the submicron characterization. At the end of the day, what's the big picture questions that we're trying to solve? Well, the microbial analysis is telling us who are the degraders and what are the trends between the different soils. Is there one particular degrader class that is present universally in the soils, which is associated to good biodegradation, and so on? The submicron characterization is telling us the bacterial habitats, the accessibility and inaccessibility considerations of the different soils, a comparison, and how they link back to the overall degradation response. What this will tell us is it will provide practitioners a predictive analysis before they proceed with cleanup operations. Canada has more than 4,000 plus oil-contaminated sites, and a number of these sites have variable response to biodegradation. Biodegradation is sustainable, it's cheap, and now I hope that after today's presentation, both you and I know how to address different responses, inconsistent responses in biodegradation, why these responses exist, and how we can have methods to address the inconsistency. Thank you for your time.
Thank you, Anirban. Our second ChangeMaker speaker tonight is Valerie Lamenta, a Master of Science student in the Department of Mechanical Engineering, working under the supervision of Professor Melanie Trottier. Tonight, Valerie will talk to us about how molten salt and the understanding of flow and heat transfer inside these kind of liquids will help us to accelerate the progress towards a sustainable energy future.
Hi, everyone. Let's talk about salt. A pinch of salt can turn a meal from a bland ordeal to a scrumptious experience. A 20-kilogram bag of salt can turn a pool from a smelly, chlorinated pond to a beautiful, relaxing oasis. A few thousands of kilograms of salt can turn solar power from an intermittent technology to a continuous, on-demand source of power. Granted, there are a few intermediate steps before we get there, and of course my research contributions. But before we dive deeper into everything that is 24-hour solar power, let's examine how we typically generate our grid-scale power. So what we've been doing for years is using thermal power plants to generate our everyday electricity. We have fuel and air as the inputs to our system. These two are burned together in order to generate heat, and that heat is used to produce steam. The steam is then fed to a turbine. The turbine powers a generator, ultimately giving us the electricity we need. And the good thing about this kind of system is that whenever we need power, we burn fuel. It's on demand. There's no need for additional storage. And we're also very good at doing this. But as we know by now, this is definitely not a sustainable way of doing things. There are two big issues here. The first being the non-renewable fuel inputs, which are typically coal, oil, and gas. And then the second issue being the greenhouse gas emissions and other pollutants that are released by the combustion of these non-renewable fuel inputs. But what if I told you that there was a way to, as we transition towards renewable, we didn't have to throw to waste all of our knowledge on the steam cycle and heat? What if there was a way to combine this cycle with renewables? Well, that's exactly what we call a solar thermal power plant, or you may have heard of it as concentrated solar power plants, or CSP. So now our problematic fuel inputs have been replaced by the sun, mirrors, and a heat transfer fluid, all the while still utilizing our highly developed steam cycle. So there are a few different kinds of CSP plants, but the operating principles remain generally the same. So sunlight is reflected by mirrors called heliostats onto a central receiver. And in that central receiver, we have a flowing heat transfer fluid. And that fluid absorbs the concentrated solar radiation as heat, and then that heat is used as the input to our steam cycle. Additionally, these kinds of systems are especially well suited to being paired with what we call thermal energy storage, which are shown by the two big tanks here. So what this means is that as the sun is shining, extra heat can be stored in a tank, and when the sun is no longer shining, well then we could use that heat to produce our electricity. So this means that we now have the ability to provide 24 hours of solar power with only 8 hours of sunlight. But we can see how our ability to provide this 24 hours of solar power is highly dependent upon the storage medium used. And in many cases, the storage medium is molten salt. So this brings us to the question, well, what is molten salt? So we're all used to seeing salt in this solid, granulated form. We put some on our food, we put some on our winter roads, we put some in our pools, the list goes on. However, when salt is heated above 220 degrees Celsius, it becomes molten, or in other words, liquid. And in this liquid state, salt is able to absorb a lot of heat, and it does so at ambient pressure. And this is very beneficial for long-term storage because now we aren't dealing with highly pressurized, dangerous systems, and we don't require large amounts of lithium as we would if we were using batteries for storage. But CSP systems aren't perfect systems. There's a lot of cost and complexity associated with pumping these large amounts of salt through these large systems and these tall towers, and also continuously tracking their temperature to make sure they remain liquid. So this means that we're now taking our inexpensive, abundant resource, the salt, and we're turning it into a costly technology. So this is why the newest iteration of these CSP plants, one of the prototypes being called the CS Pond for concentrated solar power on demand, actually combines the receiver and the two storage tanks together into one single tank. And this is what it looks like. So now what's happening is that the concentrated sunlight is being focused onto a central receiver, and that central reflector is positioned directly above an open tank of molten salt. So the molten salt is directly absorbing the solar radiation, and it's able to store it for many hours. Well, this is finally where my research comes in, because I'm interested with what is going on within that tank of molten salt. So if we take a look at a schematic of what the inside of the tank looks like. I was saying before, so we have the molten salt directly absorbing the concentrated solar radiation. So this means that we now have a hot layer of salt at the top of our tank. And this hot salt is leaving the top of the tank and going to our steam cycle. And once it comes down, this cooled down salt is now entering the bottom of the tank. And these two sections are separated by a divider plate. The geometry of the divider plate is such that it allows for flow of salt around the edges as it moves during the time of day. So as the sun is shining, this plate moves down in order to enable more energy storage. And when the sun is no longer shining, well, then the plate moves back up as more salt is being fed to our steam cycle. And the plate moves in this way because we want the hot salt temperature to remain as uniform as possible, because this is going to minimize thermal stresses later on in our system. So in order to achieve this uniform temperature of our hot salt, it was initially believed that we would need an additional mixing plate in this system. So in that CS Pond concept that I was talking about, this is the actual mixing plate that they had in there. And this is no small piece of equipment. It's over 1 meter in diameter. But what was found after testing is that the temperature uniformity could actually be achieved without even a single stroke of this mixing plate. The temperature uniformity was achieved only with a naturally occurring phenomenon. So this is great. We're able to provide continuous solar power. We know that we can remove an additional piece of equipment. But before I keep going down this CSP story, let me first recap some of the building blocks that we've seen. So we have our abundant, affordable salt. We know that we're able to build full-scale power plants utilizing this salt and even our previous knowledge of the steam cycle. And even going further into the new iterations of these plants, we know that we're able to remove mechanical equipment because of the advantageous behavior of the salt. Well, what we're starting to see here and understand is that actually all of this is conditional on us gaining a better understanding of the heat transfer that's governing the molten salt behavior. And that is exactly what I am doing in my research. But before I start throwing around all these heat transfer terms, let me first explain the 3 general modes of heat transfer. So the first mode is called conduction, and this is the heat transfer mechanism through which heat is conducted or is transported through a medium. So for example, if we take the example of heating up water on a cooktop, this would be the process by which the heat is transferred from your cooktop to the inner surface of your cooking pot. The second mode of heat transfer is convection. So this happens between a solid surface and a flowing fluid. And there are two kinds of convection. There's forced convection and there's natural convection. So if we take this example of heating up the water once again, forced convection is when the fluid is forced to move. So if it were, for example, if we were to put a spoon and start mixing in our water, well then forced convection is the mechanism by which the heat is transferred from our cooking pot to our water. And then the second is natural convection. So this is when the flow of the fluid is only due to a natural force. So it's only due to a temperature gradient. So the example of heating our water, well, our water starts to move as it's being heated because there's a large temperature difference between the hot bottom of our cooking pot and the colder top. And then finally, the last mode of heat transfer is radiation. And this is the process by which energy is emitted in the form of photons for all media. But if we're talking about heat transfer, well, then we're concerned with thermal radiation. So this is when energy is emitted by all media due to their temperature. So we have thermal radiation going on everywhere around here. But if we think about our warming up of our water, well, then every point inside the water is emitting, absorbing, and scattering thermal radiation. So in my research, I'm concerned with two of these modes. I'm concerned with natural convection, and I'm concerned with thermal radiation. So remember when I was saying that there was this great natural phenomenon that allowed us to achieve temperature uniformity and we could remove a mixing plate? Well, that was none other than natural convection. And because the salts operate at such high temperatures, well, radiative heat transfer, or that thermal radiation, also becomes a dominating mode of heat transfer. And this is where the problem lies, because we don't fully understand convection radiation interactions within the molten salt. And our current heat transfer models aren't able to accurately describe these complex interactions. So this means that we're not able to accurately predict the behavior of the salt, and we aren't taking full advantage of these beneficial situations, such as the passive mixing. Therefore, my research goal is to characterize these convection radiation interactions by utilizing a non-invasive visualization technique. And my research can be broadly separated into two big categories. So the first, and what I've done so far, is that I have to prove the viability of the experimental technique that I'm trying to perform on the salts, because oftentimes in molten salt experimentation, what people do is they use a surrogate fluid. But that doesn't work because my entire objective is to apply an experimental technique directly on the molten salts in order to get the most accurate results possible. And then once I've proven the viability of my experimental technique, well, then I can start playing with my different heat transfer conditions in order to truly isolate natural convection and see how thermal radiation will affect this. So the technique that I'm using in part one of my research, what I've done, is particle image velocimetry, or PIV for short. And you might be wondering, why am I using a fluid flow experiment to solve a heat transfer problem? Well, if you remember when I was explaining natural convection, which is a mode of heat transfer, it's the one driving the flow. So here the flow and our heat transfer are highly coupled. And the PIV technique is not new by any means, but it's never been applied directly to molten salt before. Some people have cited the high temperature of the salts, others have talked about the corrosive environment. Well, taking all of this into account, what I was able to do in the lab was actually build this entire setup, find materials that could work with the molten salts in order to perform and to prove the viability of PIV being done on molten salts for the very first time at a bulk temperature of roughly 400 degrees Celsius. And let me show you what that looks like in my molten salt test section. So what you see here on the left is my raw video. So these are little light scattering particles that the salt has been seeded with in order to perform the PIV analysis. And once again, these particles are moving only due to the temperature difference between the hot bottom of my crucible and the colder exposed surface. And then after having applied a processing software where I'll get my final PIV video, where what you see is the velocity vectors of every point in the salt in real time. And this is already a great contribution to molten salt experimentation because, as I said before, this had never been done on, PIV had never been done on molten salt before. And although I'm very happy with these quantitative results, well, now I'm interested into the quantitative aspect of everything. So that brings me to my heat transfer analysis and playing with my different heat transfer configurations. So this is the work that's ongoing in the lab right now, where I'm playing around with different parameters in my molten salt test section. So I'm playing around with the geometry of my crucible, with the insulation, my heating setup. And this is all, once again, in order to truly be able to see how thermal radiation and natural convection will affect each other. So looking at one frame of this PIV and everything that's going on in the lab, it's maybe not clear how all of this ties back to a system containing thousands of kilograms of salt. Well, from my PIV experiment, I'm able to obtain a lot of fundamental data on the molten salt. I can gain information on the velocity fields, I can gain information on the formation of convection cells, on the onset of turbulence, and even on the intensity of that turbulence. And this is all data that goes a long way in helping our understanding towards natural convection and how it behaves with thermal radiation. And this is essentially exactly the passive mixing that's going on in our large-scale system. So this means that we're now, with this experimental data, better able to model and to predict our full-scale systems. We can improve their performance, we can improve their longevity as well. And this is leading us towards cost-effective 24-hour solar power. And even going beyond solar, and if we think about the new generation of nuclear reactors, well, these new reactors are meant to be smaller, they're meant to be modular, and most of all, they're meant to be safer. And a key component of this increased safety is actually natural convection of the reactor coolant, because the goal is to implement these passive safety systems, whereas in the event of a loss of power, so no pumps, no mechanical equipment can work, we still want our reactor coolant to be circulating and removing the heat from our core. And as you'll have guessed it, well, in many cases, molten salt is the primary coolant in a lot of these new designs. So whether we're talking about concentrated solar or the new generation of nuclear reactors, we can see how important it is to obtain fundamental experimental data on molten salts. It allows us to test and validate our systems. It allows us to cut down on costs by eliminating extra mechanical equipment. And it allows us to build trust around these innovative technologies. So as we strive to deliver 24/7 renewable power to everyone around the world, we can remember that we don't need to throw away all of our past knowledge of thermal power plants and older technologies. But we do have to keep bringing forward diverse energy solutions to meet our growing global demand. And to me, better understanding molten salt behavior seems like a pretty good place to start. Thank you.
Thank you, Valerie. So our final speaker tonight is Galih Suwito. He's a PhD student in the Department of Mining and Materials Engineering, working under the supervision of Professor Ned Kitoriano. Tonight, Galih is going to explain how integrating photonics inside our silicon chips can help reduce the carbon footprint of our cloud data storage. Galih.
What comes into your mind when seeing this? If you are thinking about that food, that sushi, you are not alone. I'm thinking about that sushi, especially that sushi photo file. Where will that sushi photo file will eventually go? Well, it can probably be posted as a post in Facebook or Instagram, or maybe as a tweet, or compiled as a video for TikTok, YouTube, or maybe simply end up stored in a Dropbox. You name it, right? The point is that that photo file will end up somewhere in the cloud, a place we are taking for granted today, but relied on so much on our everyday life. Now, how if I tell you, as we exchanging more and more photos in the cloud, we are actually wasting more and more energy inside the data centers, the actual place where the data exchange is happening. And by 2030, the total energy consumption due to these data centers will reach up to 1,200 of terawatts-hour, with 50% of it will be wasted. This is a really big number, and already twice of Canada's national electricity consumption will be used solely for the data exchange. To understand why data exchange takes so much energy, let's see how our data travels between our gadgets and the cloud, where we're exchanging photos, say, among our friends. When talking about data exchange via internet, basically we are talking about a two-way communication between our gadgets and the clouds or data centers. Back in the day, copper wire cable was used to distribute the internet, much like telephone cable connecting our homes and the data centers. And these data centers are nothing else but bunches of powerful computers called servers that interact to each other to perform computation requested by us. And the fact that it uses copper wire to connect to each other makes a lot of power actually dissipate as a heat. As demand for the internet increases, more and more computers are required inside the data centers. This makes data centers become hotter and hotter. Remember, how hot is your laptop, say, after you play your favorite game? And try to imagine how hot is these data centers where we have millions of computers connected to each other at the same time. Luckily, as time goes, those copper wires distributing the internet got replaced by optical fiber. This lowers the energy consumption, reducing the cost, and makes faster internet possible. One thing that is very concerning, though, those copper wires inside the data centers, they are still there. We will come back to this, but it needs sophisticated air conditioner or AC system to be installed inside the data center building. This makes data centers consume much more energy because 40% of this power will be used for this AC system. This is how the actual data centers look like, with one of those dark squares correspond to one computing unit. You see, only with the cabling, it has been so messy. And remember, this forest of copper wire requires 40% of the total data center's power consumption. So now, to understand why the data centers still keeping these copper wires, the ancient technology, instead of changing to optical fiber, let's think about how does it take to connect two computers via optical network. Our data inside the computers are essentially electrical signals forming arrays of zeros and ones. And to transmit this optical signal, electrical signal via optical fiber, we need sort of a translator used to convert electrical into optical signals or vice versa. This equipment is called transceiver, which need to be plugged inside each computer. Inside a transceiver, what we have is basically a laser to transmit optical data and optical sensor to receive this optical data. When transferring a file, for example, what we are doing is basically input our electrical signal into the laser that makes, for example, 101010, that becomes on-off, on-off, on-off for the laser. And this blinking of light then transferred via optical fiber and received by the optical sensor on the other part of the network. And you see, this means that each computer needs to have laser and sensor. The problem with this is very clear. One computer needs to have one transceiver. Remember, we need millions of computers, that means millions of transceivers to be installed. This becoming impractical concerning the cost of installing and operating those millions of transceivers. And essentially, if you remember, in our data centers, we just don't have any more space. This is the big problem I'm going to solve. I want to make those transceivers so small, these lasers and optical sensor, I want it to be so tiny and make it place inside our computer chips, which are based on silicon materials. This will do the following things: solving the energy problem, solving the space problem, reducing the cost because the cost of the materials will get reduced, and also it will make the faster internet possible because everything now will be in the speed of light. For a material scientist like me, this idea of devices integration turns into this materials integration problem. In our case, how to grow indium phosphide crystal, which is a basis of laser, and germanium crystal, which is a basis of optical sensor, on a silicon substrate. For tonight, I'm going to focus on the optical sensor part and save the discussion of the laser part for another day. So here I listed 3 main optical sensor materials. silicon, germanium, and indium arsenide, and how it suits with applications in optical communications, which is based on infrared radiation. First, silicon. Silicon is surely inexpensive with high degree of integrability, but it suffers with very little performance when trying to detect infrared radiation. Germanium and indium arsenide, on the other hand, they have been used for decades to realize detection in infrared radiation. But they are expensive and hard to integrate to silicon. For those of you who are material scientists, when I was talking about integrability, this is something related to the lattice mismatch, and performance is related to the bandgap energy. You see, between germanium and indium arsenide, germanium has a slightly better price and better integrability on silicon. That means if we can work on the integration problem of germanium on silicon and make the sensor so tiny, so reducing the cost of fabrication, we can actually make all these three metrics by using germanium grown on silicon. So now I will tell you how germanium can be used to detect infrared radiation. This is the band diagram of germanium with incoming infrared photon. This infrared photon can excite electron into the conduction band and creates a hole in the valence band. If the electric field is applied on the band energy, this band energy is getting banded and forming sort of like a subatomic slide, if you like. And this subatomic slide can make electrons and holes slide and flow. These flowing electrons and holes are essentially electrical signals that we detected. Of course, this picture assumes that the germanium crystal is so perfect without any imperfections. In reality, imperfections in the crystal create unwanted energy levels, and this energy level could disturb the flow of electrons and holes. For example, let's consider if we have a single imperfection level near the conduction band edge. This level could disturb the flow of electron because electron initially flow, but it can jump down and actually trap in this level. That means the electrical signals that we counted will get smaller. This is considering only a single imperfection. The problem is when we grow germanium on silicon, which is commonly occurred in vertical direction, atomic imperfections are generated that looks like bunches of half loops inside the germanium layer. And this, you see, this happens because lattice mismatch between germanium and silicon. These half loops looks like the following in electron microscope. And we have seen how these imperfections will degrade the performance of our detector. So this is a really challenging problem in the community. And in the laboratory, we ask ourselves a question. Can we make the very first half loop of imperfection and make it extended and make it reside in the bottom at the interface between these two materials, other than creating another half loop, another one, another one? Our hypothesis is that by growing the germanium crystal in horizontal direction can do just that. And here is how we tested our idea. To grow the crystal laterally, we prepare crystal growth templates we called microcrucible. This microcrucible composed of a capping layer and a gold catalyst. Okay, so you see, this works just like casting, but casting, so tiny casting in microscale dimension. This is the actual microcrucible on top view under electron microscope. You see, to get this tiny, tiny dimension, we need to use sophisticated microfabrication techniques. And this include PECVD, which stands for Plasma Enhanced Chemical Vapor Deposition, to deposit the capping layer materials made of silicon dioxide and silicon nitride with the help of plasma. As we introduce this microcrucible with germanium precursor gas at 375 degrees C, we can actually make the germanium to crack preferentially on the gold catalyst, and this results in the nucleation of crystal inside the crucible structure. So as we expose more and more germanium, the germanium gets thicker and thicker, and because of this presence of the capping layer, this germanium crystal will force to grow in lateral direction. So with this, we can make the germanium to grow in lateral direction as we want it. And this makes the very first imperfection to extend it and residing in the bottom of the interface of these two materials. As a result, we can get a very high quality of germanium directly on silicon substrate. You see, as we grow from left to right, our imperfection is staying in the bottom at the interface of germanium and silicon. So this is really, really interesting result we got. And furthermore, we're also able to control the size of the germanium film by controlling the size of the gold catalyst. And if you have friends which are chip designer, this is a really big news, because in reality, in the chip design of optical circuits, we need those optical sensors and lasers to have precise dimensions. And we can control the size by controlling the gold catalyst size. In the slide, the experimental data shown in the blue dots, and the red curve is our model. You see, there is a really strong agreement between our experimental data and our theoretical model. So this demonstration have shown a possibility that our technique can be used to make optical fibers possible to be installed inside the data centers. And this way, we no longer need those cooling systems worth of thousands of terawatts of electricity. And furthermore, we can change all the copper wires in your smart devices, your laptop, your mobile phones. We can change to optical fiber. And this not only exciting because it's energy efficient, but it will make a light speed optical computing much, much more closer to reality. Thank you very much for your attention.
Thank you, Galih. So now we would like to invite all the three ChangeMakers back up on the stage so that we can start the Q&A session.
Okay, good. So hi, thanks everyone for the interesting presentations. So actually I got a question for Anirban. So first, is there a way to increase port connectivity on a field scale? Like if the field has a problem in port connectivity? And the second part of my question, if this is something not feasible, like if bioremediation is not a good option, what's the second best option to clean the field? Is it chemical or physical or a combination of both? So thanks.
Right, okay, thanks Galih for the question. So the first question, very interesting. How can you increase the pore connectivity? It's very simple. You have to mix the soil. Like if imagine it's a bunch, it's very constricted network. Like if you till the soil, if you break these aggregates, that's going to kind of increase the connectivity, either dislodge the pores, or even the spores that are like very, very densely connected is going to open them up. So that's what you want. You want the space to open up for them, for the bacteria to access. Second question, alternative, if bioremediation is not at all possible, I would still try to do like a hybrid between a physical, I would not use chemicals, like no chemicals, because they are like really bad. Still, physical is like more towards the cost, so that's also okay. I would use that, but I would try to like make a hybrid physical and biological, but no chemical, like definitely no. Like that land is useless after chemical treatment. So thank you for the question.
Hi, so my question is, because you showed that different kind of bacteria act on these oils in a different way, right? So you are saying that, for example, the blue bacteria, if we increase their numbers because they are good at removing the oil, it's going to be beneficial. But I'm not a biologist, but I have an aquarium, so I know that if you, like some bacteria will eat up something and then they will start ruining another thing. So you need to maintain a balance. But here you are like playing with the nature, you are giving them more food, maybe to grow more. So will it have an impact on other things? For example, you grow too much of that bacteria?
Perfect. Perfect. So that's exactly, so he has raised a very important question. So what's wrong? So we are adding nitrogen and phosphorus, right? So I should have mentioned, don't add too much of nitrogen and phosphorus. Look at fertilization that's happening. Like you dump it on the soil, probably the bacteria eat like 1 or 2%. Everything else goes into the water, the soil, it disrupts the ecology. So you're correct. The lowest possible that's to be added, that is just enough to stimulate them and maintain the CNP balance. So that's something. That is like the sustainable implication that's very important. So previously, this was not very well looked into, but now people are realizing that at least the paper that we submitted that has this analysis from a number of studies from across the world where we showed that this is a pattern people tend to use, but they never report that. They don't have that knowledge. So yeah, that's the thing. Thank you.
Thank you. Oh, please wait for a while. The mic is coming. Thank you.
Hello, Valerie. So I'm really happy with the concept you came up with because of this thermal power plant. These are not good. Yeah, actually fine. So I actually have one doubt, like where we are using those salts to create pressure. In thermal power plant, we generally depend on the pressure and the temperature, right? So if we use the salt, there are some faults or something where we need to decrease or increase the pressure level or the heat level, because those two are dependent. So how can we do that using that container? I mean, is there any mechanism of creating more pressure? Sometimes like the temperature goes beyond 45 degrees Celsius, sometimes at the top point inside the boiler, right? And the second part is, if we use salt just to create heat and the pressure, will there be any chances of corrosion? Because it may damage the turbine blades, right? Yeah.
Thank you for your questions. So the salt itself will remain at atmospheric pressure as it's heated. So in terms of that part of the system, the pressure doesn't really need to come into play. Like the rest is still the same. Like the turbine, the salt is just used as your heat transfer fluid to create your steam afterwards. So in terms of the salt aspect of it, then pressure doesn't really play a huge factor. But yes, as you were saying with your second question, the temperature differences, that is something that we have to take into account. And so my research was done with nitrate salts, which are often used as these heat transfer fluids. And they do very much have a maximum temperature limit. And that's why work in our lab is actually looking at higher temperature salts, because then you can minimize, well, you have a larger operating range where you're not running into salt degradation and stuff like that. But another concern, obviously, with the salt is that it's not compatible with every material, and we definitely saw that in the lab, and that's something that they're seeing at the large-scale plants as well. So there is an aspect of cost that is related to just the materials that need to be used, and that's kind of why right now, like, we're trying to simplify the designs of these systems and not have these huge systems of pipes, because our levelized cost of electricity isn't yet on par with photovoltaics, for example.
Thank you for the question. Yep.
Thanks, Monica. So I'm kind of blown away and kind of embarrassed about my own speaking ability now after listening to the three of you. I actually have a question for each of you, and I hope you don't mind if I'll just throw it out one after the other. In terms of the salt, you're not taking advantage of any phase transformation at all in this case. So what's the temperature range that you're working with the salt?
So the nitrates, the nitrates that I'm working with will become molten at 220 degrees Celsius, and we'll start seeing some salt degradation around, I think it's 550. So there is that temperature range. But as I was saying, like, we're trying to also push our work into further salts, which have even larger operating ranges. Okay,
I was just wondering, what other materials are there? Are there something other than salts that you might consider for that?
For your
heat transfer fluid?
Yeah, so what's used in industry now, it's either salts or they'll use what we call thermal oils. So they might be a little bit more easier to work with in terms of corrosion and all these things, but their operating range is not as large as the molten salt.
Okay, all right, thank you. I've got a question related to soils. So I found it really interesting. So measuring the porosity and the connectivity essentially between it. Have you thought about flipping this around and actually saying that there are certain sites around certain activities should not take place because they're more vulnerable to long-term contamination? So in other words, can you characterize the soil at a site and say this is not a place where we should be doing these kind of activities with diesel oil, just to kind of set boundaries on where these activities might occur?
Yes, before the incident, that's a very good question. Before the incident, yes. But again, between this analysis and the actual operation taking place, the time in between, so weather events might happen, there can be a lot of things happening in the soil, so that might change because any industrial operation will be large scale, and because it will large scale, it will impact a big area. So actually, if they do a lot of digging around and all that, maybe the soil will actually become very loose. And then, of course, doing the industry is not good over there, but they're like, oh, we have to have diesel plants, for example. So then immediately before they set it up with a reasonable time frame, if we then it's useful. Then we know, okay, if set it up, maybe as soon as they start operations, we start cleanup as well. Because that's okay. So, thank you.
I guess the last question with respect to the germanium.
Okay.
So in your original table, you talked about in order to make this work, you're trying to increase the interconnectivity, I guess it is, the effectiveness of it, but you're also trying to reduce the cost. So it's really a question about, it's really interesting approach that you've got in terms of growing the component horizontally. Do you think that could be scaled relatively easily so that you can also make sure that the cost drops down as you were counting on?
Yes, that's a really good question and a very practical one. This technique is used the commercial chemical vapor deposition, in which used by the semiconductor foundry. Intel, everyone used CVD. So this can be scaled up, that's for sure. And if you notice, we used gold catalyst, which may raise a question. But this is lab scale. We use gold because it's inert. But then we can also change to silver, nickel, which is much, much cheaper. So this is, in terms of scalability, sure, it's very feasible.
Thank you. Much appreciated.
Yeah, thank you. Thank you so much. Well, I'll just indulge and ask you all a question. So first for Mr. Anirban about in the north, in these remote communities, I'm just curious, how much involvement do you coordinate with the locals? I mean, in the local communities, and how much of your work are you communicating with them, the results, and sort of is there collaboration in that sense?
So we work with a major energy corporation here. So we coordinate with the chief of the environment. When I joined, the first question I asked was, am I going there? So no, that didn't happen, unfortunately. There was a bonus. We did get to see pictures of sites when she came, but it's mainly I do the work, and we present to our collaborators, and they inform on-site practices there. So that's how it happens. We know which sites they are cleaning up now. We know what's in their schedule. So based on that, we do the experiments. But that's the collaboration we have. I wish I could go there, but.
Thank you. Yeah, for Valerie, you mentioned about other groups using surrogate fluids, and that it was kind of this was new, doing PIV and molten salts was new. What was, I guess, just curious more about what was new about it, or what were the other problems in the way before people were able to do the measurements in that way?
Well, good question. That's something that my lab mate and we were both very surprised as to. It seems almost too obvious, why has no one done this before? But for lack of a better answer, it's just no one had. Oftentimes what people will do is that they'll do kind of a two-phase analysis where they will do their heat transfer analysis on the salts, and then the fluid flow analysis they'll do on a surrogate fluid who would have similar properties to the salt. And what we're trying to do is to really get the best broad picture by doing this at the same time on the salts directly.
Final question. Thank you. You mentioned, Galih, about the wires are consuming 40% of the energy. That's what I understood. I was surprised, I guess, to hear that. It's kind of like transmission losses or something like that. Right. So I'm just curious, and I guess your solution is great, but it's probably a long way in the future. So I'm wondering, what else can be done for that? Is there any other way to reduce those losses rapidly and cheaply?
Right. So first of all, let me straighten it a bit. The power loss is 10%. But because of this loss, we have heat inside the data centers. And this heat requires 40% for cooling system. So in total, 50% is wasted. Actually, this is double waste issue, sort of like. So what is being done now is actually people for smaller scale data centers in which the data center is not so dense with those servers and cabling. They try to use optical fiber if the distance between computers is so long. But for super dense data center, in which currently we have millions of computers, I don't see any immediate solution for that, except people try combination of copper wire alloying with other materials to basically reducing the amount of electron scattering, basically would contribute to this loss. Very good question. Thank you.
Yeah, thank you. Yep. If there's no more question, I'll, yeah. Yeah, you have a question? That's good.
Okay, so Anirban, sorry. So you mentioned this in your talk, but you said that you replicated the field conditions in your experiment. But I'm wondering which season and whether you looked at different seasons. I imagine that, you know, we're up north, but there's still seasons. Yeah, so we could just comment on that.
Excellent question. So I replicated the summer season because winter, it's frozen, permafrost. It's slightly difficult. So majority of the bioremediation activities happen in the summer when the ground has thawed. So we analyzed last 10-year temperature data from NASA, and we did calculations to find a statistical approximate. That is the temperature that we tuned in our temperature controller in the incubator. So this is, and across all the sites, of course, there is a certain level of variation. Like I do it at 7 degrees. So it can be maybe 6.5 or 6 for some, but considering that variability, we programmed the controller to have a ramp kind of a thing. But yeah, it was summer temperatures because that's when most of the activities happen. Good question.
Yeah, thank you.
I have another one for Valerie,
yeah.
Because I know other people are thinking it. So when you did your experiment, right, your setup is such that your heat is coming from the bottom on your reactor setup, but in the field, the sun, the energy is being concentrated and fed into the system, for lack of a better word, from the top. So do you expect that there will be, like, do you have to make an adjustment for that, for the data that you're looking at, or how does that relate when you look back at your fieldwork?
So thank you, very good question. That kind of ties into almost another experiment that's going on in our lab. So I'm focusing really on the heat transfer. So when I'm talking about thermal radiation, it's really the one that's within the salt itself. But yes, you're absolutely right, that in a real system, well, then we have the solar radiation that's coming in. So that's another form of radiation. And the reason why I'm doing heated from the bottom, it's because in the actual setup, the salt is semi-transparent to this, this solar radiation. So actually, volumetrically, it does absorb a bit, but the bulk is absorbed by that divider plate. So that creates kind of that heated from the bottom condition. But yes, my experiment is more of a fundamental heat transfer experiment, but then we also have a piece of equipment in our lab, which is a fake sun, a solar simulator. And work is going to be done with directly irradiating the salt with that lamp. So that'll be more of a practical application experiment as well. So we kind of have these two projects going at the same time.
So I'd like to invite the Associate Director of TISET, Professor Jeff Bertolson, to come up here to say a few words of closing. Thank you very much.
Thank you. Well, first I'd like to thank, it's so great to be here in person after 2 years. The pandemic started 1 week after we were ready to go, and we did our dress rehearsal in 2020, and we're ready for Sedtalks, and then 2 days later we were shut down. And so after 2 years, it's amazing to be back here. I'd like to start by really thanking our 3 ChangeMakers tonight. I mean, they put in a huge amount of effort over 5 months to develop and hone these talks. I think, you know, the results speak for themselves. And really, we wish you all the best as you complete your projects and represent McGill going forward. On behalf of the ChangeMakers, I'd like to thank their supervisors because they've given them leave to take on this extra responsibility and to go through this program and put in all those extra hours that takes away from the research, but I think the rewards are well worth all of that effort. I'd like to thank WSP for their support of the program and of TIZED as well, and of Mr. Eric Pazel for his time today. And on behalf of all the presenters, I'd like to extend a special thanks to the selection committee, the alumni ChangeMakers, our faculty and industry partners, and everyone who's given their time over the past months to give feedback to the students as they developed and honed these presentations. I'd especially like to thank Yiwei Feng for his efforts in working with the ChangeMakers over this year, and as well as serving as the MC for both the 3-minute thesis competition and tonight's event. It's the first time that I'm taking part in Sedtalks and not being the MC, so it's quite a nice change for me to be in the audience and enjoy the presentation. What really makes me proud is that this year we really saw a lot of the alumni ChangeMakers stepping up and acting as teachers, coaches, and mentors to the new students. And I think that's great to see that it starts to perpetuate itself. They start to become a community that gives back. And that makes me very, very happy, because really the name ChangeMakers was chosen when we started this program because we want students who go through this to become agents of change in the world afterwards. And I think making that difference here within the program itself is the first step on a long journey there. This wouldn't be possible without the support of Teaching and Learning Services at McGill, and specifically Andrew Churchill, sitting over here, who spent countless hours with the students. Yeah, I think we can give it more. Throughout the program. Also need to thank McGill Media Services team, who's been here supporting and helping us set up all of the event, and as well as the TIZED staff for all of their efforts in making tonight's event happen. The ChangeMakers, as Dean Nysel mentioned, have presented just a small snapshot of the great research that's going on in McGill, in the Faculty of Engineering, in the area of sustainability. And so I hope that for those of you in the audience who are students, this might give you a taste and an inspiration to join the program and to celebrate your research with us in the coming years. So on behalf of TIZED, I'd like to thank everyone for joining us tonight. It's been a real pleasure to see you all here, and thanks for being part of our 2022 Sedtalks. Good night.